Welcome to the tutorial on design of sequence detector. In one of the previous tutorial we have seen the sequence detector design when we looked into the construction of state diagram. In this particular tutorial we will particularly focus on the design of sequence detector, wherein we will consider a single numerical question and try to design the circuit for both Mealy and Moore machine. So the question goes in this form: design a circuit that examines a string of zeros and ones applied to the input X and generates an output Z equal to 1 only when a prescribed input sequence occurs. It is assumed that the input X can only change between the clock pulses. Specifically, design the circuit so that any input sequence ending in 101 will produce an output Z equal to 1 coincident with the last one. The circuit does not reset when output 1 occurs. So they have given us the block diagram wherein they have shown that X is the input, Z is the output, and the clock is being provided. The most important thing that we need to note here is that Z will be equal to 1 when the input sequence ends in 101. So when we consider an example of a string, we should see to it that whenever the sequence ends in 101, Z is equal to 1. So for the first one, let me design the circuit using a Mealy machine. So I have considered a general string, a sequence of binary numbers, zeros and ones, and I have seen to it that I have a sequence wherein 101 is there, so that I get an output Z to be equal to 1. So wherever the sequence ends with 101, I have Z to be equal to 1. So even if I consider this particular sequence, I have Z to be equal to 1. Now initially, to start with the design of the sequential circuit, we do not know how many flip-flops are required for this. So we will simply designate the circuit states as, say, S0, S1 and so on. And then later we will try to assign the flip-flops which will correspond to the circuit state. So for that, we begin by constructing the state graph, which will show the sequence of states and the outputs which occur in response to different inputs that we have specified. So initially we start the circuit in the reset state, that is this point. And we are going to designate this as, say, S0. So if you are in the state S0, you get an input X to be equal to 0 and the output is equal to 0, you are going to move back to the same state. Now, for the two intervals, this one and this one, it's going to remain in the same state. So next you have an input 1 and an output 0. So when you receive an input 1 and an output 0, you are going to switch from S0 to S1. So you have completed up till here, that is this particular time instant. So this first graph that you see here will correspond to up till the time interval 0 to 2, because whenever you receive a 1, you will change from state S0 to S1 with an output 0. Next we need to check what will be the next input sequence. So when you are in the state S1, that is this particular state, so even in this case 1 0, so there is no change. So you are here and this instant, so you're going to remain in the state S1 itself. So the next two possibilities that you can have is these things, 4 and 5. So now you are in the state S1, you receive an input 0 and output is 0, you've moved to the state S2. Whereas you receive a 1 and you have sent an input 1, you move back to the state S1. Now what this means is that you have correctly received the sequence 1 0 appropriately, because as per our consideration we have said that the state machine will produce an output 1 when the ending sequence is 1 0 1. So we have correctly received the sequence 1 0 1. So once you are in S2, that is this point, you are going to move back to S1. Now you might be wondering as to when you have received the sequence 1 0 1 appropriately, why is that you have moved back to the state S1 and not to the state S0? One of the reasons is because in the question it is mentioned that you are not supposed to reset when output 1 occurs. So that is the reason that we have moved from S2 to S1 when we received the correct sequence ending with 1 0 1. So that is the reason. Otherwise we could have directly moved from S2 to S0 wherein we could reset. So till here we have completed, that is up till this particular point. Now if you look at the state diagram is still not complete. You have further sequences that you need to look into. So next we'll move to the sequence wherein you obtain a 1 and the output is 0. So in this case, if you obtain a 1 and the output is 0, you are in the state S1 now, because after receiving the sequence 1 0 1 you had reached S1. So you are in the state 1 and you received an output 0, so you are going to remain in the same state, that is this point, and next sequence is again 0 0. So you are in S2 and with an input 0 and output 0 you are going to reset back to S0. In this case you can reset back to S0, that is because here the output Z is not equal to 1. So here we are going to stop. So this is the complete circuit diagram that we have obtained. Now from this state diagram we can obtain the transition table and the state table. To obtain the transition table, as you can see, we have a total of 3 states: S0, S1 and S2. And if you look at the Mealy machine was represented with an arc which was in the form X bar Z, where X was corresponding to the input and Z was corresponding to the output. So when you consider the state table, we will consider the 3 states S0, S1 and S2, and X can either be 0 or X can either be 1. The present state is X is 0, X is 1. You are in the state S0, X is 0, you are going to be in S0. When X is 1, you are going to move to S1. So X is 0, X is 1, 0, 0. That is, this corresponds to basically the present output Z. Z, as you can see, here is 0, here also it is 0. So this is the next state, this is the present output Z. You are in the state S1, input is 0, so you are going to move to S2, input is 1, you are going to move to S1. In both the cases, output is 0. You are in S2, you are going to move to S1 if input is 1, else you are going to move to S0. And here output is going to be 0, 1. From the state table, we will draw the transition table. Since there are 3 states, we will assign the 3 states to be of the form AB, and the 3 states need to be represented in the form of 2 flip-flops, so 2 variables would be required. So 0, 0, 0, 1, 1, 0. So that is what is being represented. So this becomes your state assignment. So this state assignment has been given to this particular state table in order to obtain the transition table. So we have represented in the form of 2 variables, and S0, S1 and S2 is being replaced with 0, 0, 0, 1, 1, 0, and the present output Z is retained as it is. So this is the transition table that we have obtained. One important thing that you have to observe in this particular state graph is that for a single input variable, each state must have 2 exit lines, one for each value of the input variable. As you can see, here you have input 0, input 1, input 0, input 1. So each state should have 2 exit lines for different inputs. Then only the state diagram is complete. Now from this particular transition table, I can draw. So this Karnaugh map will correspond to the next state graphs, wherein I have considered a 3 variable Karnaugh map, because if you can see the next state table that we had drawn, we had A, B, and then we had X. So looking at those parameters, you have A, B and X. So when you look at the variables, how do we specify A plus and B plus? So if you can see, this next state corresponds to A plus and B plus in the transition table. So you need to look for the variable corresponding to logic 1. So if you look at that, you can see that 1 is present only for 0, 1, 0 case, and for the case of 1, 1, you have don't care terms. That is because 3 states were present, S0, S1 and S2, and we have labeled only for 0, 0, 0, 1 and 1, 0. For the case of 1, 1, we haven't labeled. So because this is not labeled, this will be considered as a don't care term. So of anything of the form 1, 1, 0 or 1, 1, 1 will be considered as a don't care term, represented as a X in the Karnaugh map. So similarly, if you look at the state table and the transition table, if you want to represent B plus, you have to look for min term, and the min term is 1, 1, 1. So you will have 0, 0, 1, 0, 1, 1 and 1, 0, 1. So 0, 0, 1, 1, 0, 1, 1 and 1, 0, 1. Here again it is a don't care. Finally, if you look at this transition table and the state table for the variable Z, you will be able to see that only for A, B and X equal to 1, Z was having a min term. So hence you will get A plus to be equal to x bar B, B plus to be equal to x, Z to be equal to XA. So these are the three equations that you obtain for the next state graph so that you can draw the sequential circuit. The complete sequential circuit, if we have to draw, we have to consider flip-flops. Now input to these flip-flops we have obtained from the expressions that we have considered for the various Karnaugh maps. So we had obtained the expressions as A plus to be equal to x bar B, B plus to be equal to x, and Z to be equal to x into A. X is the input, Z is the output. So these equations have to be corresponding to the input that will be given to the flip-flop. We will consider this to be given to the D flip-flop, that is the first one, DA, and this to be given as an input to the second flip-flop, that is DB. For both the flip-flops, we need to provide the clock. So that has been provided. Then DA, say this is DA, the first flip-flop, that will be equal to x bar. So x is provided with the NOT gate into B. B is this one and given to the output, that is D, first flip-flop. So this corresponds to the flip-flop with DA and DB. For DB you are going to give D to be equal to just x. So DB is nothing but equal to x and Z is equal to x into A. So that completes the design of the sequential circuit using the Mealy machine. Next is the design of the Moore sequential circuit, and in this case we are going to represent the inputs over the arcs and the outputs will be represented within the node along with the states. So for this example also we are going to consider the same question that we have considered previously, that is this question, wherein we are supposed to consider a string of zeros and ones and the output Z will be equal to 1 only when a prescribed input sequence occurs, and the sequence ending in 101 will produce an output Z is equal to 1, and the circuit does not reset when output 1 occurs. So for this case as well, the same sequence, same string of sequence will be considered, and we will try to generate the Moore machine for this case. So what I'm going to do is I will just write the sequence again so that it's easy for you to understand. X is equal to 0 0 1 1 0 1 1 0 0 1. Z is equal to 0 0 0 0 0 1 0 0 0 0. So to begin with the design of Moore sequential circuit, I will consider the sequence, the same sequence which we have considered previously, and here I will begin with the first state S0. One important observation that you need to make, which is the difference between the Mealy and the Moore machine, is that in the case of the Moore machine we will be representing the input along the arcs and the outputs will be represented within the node. So we have the first state S0. If the input is 0, output is 0, you will move to the same state S0. So this is a repetition, I'm not going to deal with that. So the next input is 1, input is 1, output is 0, you are going to move to the state S1. You are in the state S1 now. Next you have input 0, output 0. So I'm going to move to the state S0. So input is 0, output is 0. Now next we have the state S2, which you are already present in. The input is 1, output is 1. So you will move from S2 to S3. Input 1, output 1. So the next sequence that I have is input 1, output 0. So input is 1, output is 0. So you are going to move to state S1. So from S3 you have moved to the state S1. Now if you observe here, in this case, it would be the point where you have ended up with the generation of the sequence 1 0 1 and you got an output Z is equal to 1. So this is the ending point. So now input 1, output 0, you are in the state S1. One of the reasons why you have moved from S3 to S1 is the same reason that you have used for the Mealy machine, wherein it was mentioned that you're not supposed to reset. So that is why you have moved from S3 to S1. Now input is 1, output is 0. If you are in S1, you will move to the same state. Input is 0, output is 0. You will move to the state S2. So these two are complete. Next, you have the state S2, wherein input is 0, output is 0. You will reset. Finally, to draw the state table and the transition table, the state table and the transition table will have a total of 4 states, unlike the previous one, wherein we considered only 3 states, S0, S1 and S2. So here when we are going to assign the variables, we will assign the variables as A, B, and we are going to represent them in terms of 2 variables 0, 0, 0, 1, 1, 1 and 1, 0, and map them according to the state table, and this is what we get. Now using the Karnaugh map, you need to simplify, and after simplification you will get the expressions for A plus, B plus and the expression for Z. Based on this, you will decide that you will be using a total of 2 flip-flops, and DA will be equal to A plus, DB will be equal to B plus, and Z will be the output. So the circuit that you obtain will be based on the equations that you obtain for 3 of these cases based upon the transition table. So this is going to be left as an exercise for you to draw the machine or the sequential circuit for this particular design.